Hello guys, welcome to a supplemental video that's going to cover some more kinematics examples. So we did a few examples in class today. Most of them were of the little simpler variety. So we're going to do a couple more difficult problems. We're going to do a little bit more difficult free fall problem. And then that'll be it. I'm going to try to keep this video to about 15 minutes, but it may be about 20. We will see how it goes. So we're going to do a couple of special situations with kinematics. The first kind of situation we're going to do is whenever we have two objects in motion, which is what, yes, if you were in fourth period, we did this one today with you guys. And then we're also going to do an example where we have an object, one object with two or three different kinds of motion. And then we're also going to do some free fall problems that kind of investigate in a little bit further detail what's happening with objects as they fall or whenever you throw them upwards. So let's start with the two objects example. So let's say you are a car, and again, like I mentioned before, if you were in my fourth period, we did this example together today, so you can still follow along if you didn't get it the first time, but if you're in my other periods, you definitely need to watch. So here's car A, and we'll say this car is initially at rest, and it is at a stoplight. Once this light turns green, this car will begin to accelerate. Let's say it's going to accelerate at 3 meters per second here. Let's say right at the instant that the light turns green, right when this car begins to move, a second car, car B, flies through the intersection, at a constant velocity. And let's say his velocity is 20 meters per second. So the question that is going to come up is where and when will car A catch car B? Because if you think about it, this car is not moving initially, right? It has to slowly, it's accelerating. It has to eventually increase speed until it catches up with this second constant velocity car. So I want to know where and when will car A catch car B. So the first thing we need to realize is that in this problem we have two objects. So anytime we have two objects, we're going to need two sets of equations to help us describe what's happening. So for the first guy here, he is moving at a constant velocity. So if we have a constant velocity, we only have one equation that will work for that object, and that is our constant velocity equation. Now, for our car A, any of our kinematics equations that we learned today will work to describe what he's doing. Why? Because he is accelerating. So anytime something is constantly accelerating, we can use these guys to help us figure that out. X naught plus v naught t plus 1/2 at squared. Okay, So let's answer the first question of where. Where and when will car A catch car B? So when those two cars, so let's say this is car B, shoo, flew ahead, and here's car A, and it's kind of taking its time, doop, 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 it finally gets to here. When these two cars catch up to one another, their positions, car A and car B, will be exactly the same. So what I need to do is I need to figure out a way to talk about car A's position, a way to talk about car B's position, and then I can set them equal to one another. So the velocity of car B, since it's constant, is just equal to its distance over its time. So the distance car B travels is going to be its velocity times its time. Alright, so let's look at car A, back on the previous slide. So car A here, now we have some options, right? We are focused on finding position. So the only two formulas we have that have position in them are these two. We don't know anything about the car's final velocity, so we probably don't want to use that formula. It's probably going to create more headache than it's worth. So your position here, let's look at this formula. The other reason why I want to use this formula is because this formula has time in it, and so does this formula. So that's going to put all of my unknowns in the term of time, which is going to be incredibly helpful. So the position for car A is its initial position, which will just be 0, its initial velocity times time, which will again just be 0, plus 1/2 AT squared. So that means the position for car A will be 1/2 AT squared. Alright, so let's plug that into here, and let's put this into here, and we can start to see some magic happen. So 1/2 AT squared equals velocity of car B times time. Now I have a time on both sides of my equal sign, so I can cancel out the squared on this one. I can divide both sides by time, and I get 1/2 AT equals VB. Now, I don't know what my time is, but I know everything else, so I can rearrange it to solve for time, and I get 2 times velocity B over A. So velocity B was 20, and your acceleration was 3 from the previous knowledge. So that would be 40 divided by 3, which is going to be about 13.3333 is your time. Alright, so now that we know the time it takes for those two cars to actually meet up together here, now we can try to find the position. Now it doesn't matter if I use the car A or car B to solve for my position. Since they're both in the same spot, they should have the same position. So let's use car B because it's a little bit simpler. So 20 equals x divided by the time it took for them to meet up, 13.33. And that gives you a position of 267 meters. Okay, so this kind of problem solving just takes a little bit of time. And this might be the first time you guys have ever had to do anything like this. But just take it slowly, and just remember that if you have multiple objects, you're going to have multiple expressions. You're going to have one expression for each object. So here's my car A, and here's my car B. Okay, so the the next kind of example I said we were going to do with an object with 2 or 3 different kinds of motion. So I'm going to combine, well, yeah, let's combine 2 and 3 together and make our free-falling object have 2 or 3 different kinds of motion. And then that will help you guys out with that one. Okay. Couple of tips for solving physics problems. Always draw a picture. Always label your picture with givens. Those are 2 really helpful things to do. And then once you have your givens, I want you guys to really get in the habit of playing with some of the equations. And by that I mean just try something. You have probably enough information with the givens you have to start somewhere. And start playing with the equations a little bit and putting in your givens and just seeing what happens if you're unsure of where to go in a problem. That's always a good start. And then if you need my help, I can help you out and kind of steer you in the right direction. But I really like you guys just to kind of experiment with the math a little bit at first. So let's look at a rocket. It's about as artistic as I get, so that's a rocket. So the rocket is going to launch itself upwards. So the rocket will accelerate. Let's say a rocket, I'll write the question on here. Rocket accelerates from rest on the launch pad to an altitude of, what's a good altitude? We'll say 1,000 meters with an acceleration of 4 meters per second squared. The engines then cut off and the rocket coasts to its maximum height before falling back to Earth. And this is like a toy rocket, guys. This isn't like a shuttle. This is a little model rocket. Okay. Model rocket. I guess that's pretty high for a model rocket, but we'll roll with it. Okay, so it's going to accelerate from rest on a launch pad to an altitude of 1,000 meters with an acceleration of 4. And then at that moment, the engines are going to cut off, and the rocket is going to coast to its maximum height before falling back to Earth. I guess I shouldn't say the word coast because it's not really going to do that. And the rocket will travel to its maximum height before falling back to Earth. So I want to know a few things. I want to know what is that maximum height, and I want to know the time it takes for the rocket to come back down to Earth. Time for descent. Alright, so first thing we want to do is we want to draw a map to show what's happening. So rocket takes off here. It's at rest on the launch pad, so its initial velocity down here is 0. It's going to take off upwards. Acceleration is 4. Now, I know it's traveling through the air, but it is not under free fall because the rocket's engines are providing a force which is causing the rocket to travel upwards. So it's actually accelerating upwards. It's not slowing down upwards like normal objects would do because it has its rocket engines. And so its distance here, its change in x for this chunk is going to be 1,000 meters. Alright, then we have a different kind of motion happening here. where the rocket continues onward until it reaches its maximum height, and its maximum height at the very top, its final velocity here will be 0. But we have two very distinct kinds of motion here. We have a chunk of constant acceleration, and then we have another chunk of constant acceleration. But here, since the engines are no longer firing, you are under the effect of gravity, so your acceleration for the second part is -10. So I want to know, what is the height of the whole thing? So I know the height of this first part. I just got to figure out the height of the second part. So let's look at the second part, what we know. We know the final velocity is 0. We know that A is -10. We know we're looking for our change in x. So if we look at our formula chart, which I hope you guys have in front of you, you can see we can almost use a couple. We can almost use the displacement formula, and we can almost also use this guy. But in order to use this guy, I would need to know the rocket's initial velocity at this chunk of movement. So that means I would need to know whatever its speed was right here. So I can do that from the previous information, because here, from here to here, the rocket will continually gain speed, gain velocity. And so the final velocity of this first chunk of movement becomes the initial velocity for the second chunk. So let's look down here. Down here we have V0 0, A equals 4, change in x equals 1,000. We want to know, what is our final velocity? So we can actually use this same formula for this first chunk here. So let's go ahead and do that. 0 squared plus 2, 4, 1,000. So 2 times 4 times 1,000 is 8,000. And I guess that's a really fast model rocket, because that's going to be going 89 meters per second, which is pretty fast, but that's okay. We'll roll with it. I didn't practice these problems. I'm just making them up as I go along. All right, so that means that the rocket here has a velocity of 89 meters per second. So that becomes the initial velocity for the second part here. So let's erase this bottom part and let's continue on. So now we know our initial velocity for the top part is 89. So now we can do 0 equals 89 squared plus 2 negative 10 change in x. So now I'm going to do 89 squared divided by negative 20, or rather divided by 20 at this point, and that gives you a change in x of 396 meters. So squaring this, bring it over to the side, it's negative 7,921, divide that by negative 20, and the rocket went in extra 396 meters. So to answer our question, the total displacement of the rocket would be our 1,000 plus our 396, which is 1,396 meters. All right, so the next part asks, what is the time for the rocket's descent? So we got the way up, so let's talk about what's going on the way back down. So here's the rocket at the top. Now it's going to fall all the way back down to Earth. So now we know that the change in x, or the displacement, is 1,396. Since it's falling, its acceleration is negative 10 the whole time. Its initial velocity up here at the top should be 0, because it went all the way up to the top, and now it's going to fall all the way back down to the bottom and gain more and more speed. And we want to know the time. So again, our initial position rather would be 1,396. Our final position would be, sorry, this is our initial position. Our final position is 0. My bad. Okay. X naught plus v naught t 1/2 at squared. So your initial position, your final position is 0. This is the formula we want to use. Your initial velocity is 0, so that just cancels out. -10 t squared. Bring that over to the side. So we're going to do 1,396 divided by 5, and then we're going to square root it. And that gives you a time to fall down of about 16.8 seconds. All right. I hope seeing these other kinds of examples kind of helped you guys out a little bit. If you guys still have questions, don't worry. You have the ability to email me, and I will be glad to help you. I also will probably be here tomorrow after school, Thursday after school for tutorials. So if you need some extra help, feel free to come by and see me. And I hope you have a good day.